Hi, good morning, everyone. Good morning. What is the last subtopic we have done? Hi. Good morning. Good morning. What have we done? The last subtopic? We have done about Lenz's law and the questions, right? All done. Okay. So we have to start nuclear and particle physics. Are there any questions or homework? No, I think last day we completed the questions. So guys, today we are starting nuclear and particle physics right on the topic. Nuclear and particle physics. So this is the last part of Unit 4, the last topic for Unit 4. Right. Under that, the first subtopic, alpha particle scattering experiment. Alpha particle scattering experiment. Okay, right. That's it. And I believe most of you people have done this for O-levels. No? Have you heard about this?
I've heard of alpha particles.
The O-levels, we haven't done alpha particle scattering experiment. Right, fine. So guys, now listen. This experiment is used to see the nature or the structure of an atom. Okay. When initially, back then, there was no clear idea about how an atom will look like. You know what is an atom, right? Atom consists of what and what?
Protons and neutrons.
Protons and neutrons and electrons. So if you take the structure of an atom, it consists of protons and neutrons in the central region, which is known as the nucleus of the atom. Am I right? And there are electrons orbiting the nucleus. That is what you know about an atom. So how did you get to know about it? That is through the experiments which were done back then, right? So guys, at the initial stage, when there was no idea about how an atom will look like, or how an atom, what is there, what are the components in an atom, there were experiments carried out to see the structure of an atom. So one of the famous experiments out of that, which we learn, is this experiment, which is alpha particle scattering experiment. Okay. So how is this? Do you know what is an alpha particle? What is an alpha particle? A helium nucleus. So an alpha particle consists of what and what? Two protons and two neutrons. Am I right? So alpha particle consists of two protons and two neutrons. Protons are positively charged, correct? And neutrons are negatively charged. No, neutrons are neutral. They don't have a charge. So if you take two protons and two neutrons, alpha particle consisting of two protons and two neutrons, which means the alpha particle itself is positive. Is that clear? If you take an alpha particle, it is positive because it has two protons and two neutrons. Two protons are positive, two neutrons are neutral. So which means the resultant charge of an alpha particle is positive. So a beam of alpha particles is fired at a thin gold foil, thin sheet of gold. And the observations were most of the alpha particles just went through the gold sheet without any deviation. Okay. Most of the particles went without any deviation. And a small percentage of alpha particles slightly had deflection.
See,
They had
now
a
I
small,
remember, yes, we did it in always.
of course, you have done this for levels. Okay. The small percentage of alpha particles slightly deviates from its original path. Okay. And even a small percentage of alpha particles, they just go and take a U-turn, or they deflect more than 90 degrees. These were the three types of observations. One, most of the alpha particles just goes through the sheet without any deviation. A small percentage of alpha particles deflects from its original path with an acute angle, maybe 10-15 degrees deflection, or maybe a bit more, right? And there was another set of alpha particles, or even a small percentage of alpha particles, which had a deflection like this, goes towards the sheet. It doesn't hit the sheet, it takes a U-turn, a deflection more than 90 degrees. These were the three types of observations. So based on these observations, what extracted about the atom is this. Most of the alpha particles are going undeviated means it should be that the atom should be mostly having empty space. Atom should be mostly empty. So that is a reason without any disturbance, the beam of alpha particle is just going straight. Okay. So that means atom is mostly empty. So a smaller percentage is getting deflected by an acute angle, that says. Now we know that alpha particles are positive, right? Alpha particles are positive. And let's say the particles are moving like this, mostly undeviated. A small percentage is deflecting means there should be something in the middle here. There should be something
That is positive.
which is positive and making the alpha particles go away. Okay, that gives you a slight idea. Okay, there is something in the middle which is positive. Okay, because we know that alpha particles are also positive. And who is getting this 180 degree or maybe more than 90 degree U-turn? Those are the ones exactly going towards the center of the nucleus. When they go towards the center of the nucleus, they get deflected more than 90 degrees. So that tells you there is a small region in the middle of the atom which carries the most of the mass of the new atom, which is what labeled as the nucleus later on. Understood? So this is an experiment which is done to know the structure of an atom, and this is what accepted as the structure of the atom so far. Right under that? Geiger and Marsden. Geiger and Marsden.
So can you go upstairs so I can see the spelling?
Sorry,
Started.
just now started. Geiger and Marsden did an experiment by firing a beam of alpha particles. Did an experiment by firing a beam of alpha particles at a thin gold foil. At a thin gold foil. At a thin gold foil. Full stop. Majority of the particles pass straight with no deviation. Passed straight with no deviation. Full stop. A few alpha particles, alpha particles deflected by large angles. A few alpha particles deflected by large angles. Full stop. The conclusions derived based on the observations are as following. Yeah. Guys, just draw this diagram for your understanding.
Sir,
Yes.
so this person who wants you to go back to the previous page.
Okay, after the drawing. Did everyone get the change? Again, this last class.
What did we do last month?
Electromagnetic induction.
We didn't start party.
No, we are starting today. Okay. Right, guys. So you can see some alpha particles, they have a deflection, a small deflection. And here you can see in this diagram, the deflection is a bit more. That's the reason that beam of alpha particles are closer to the nucleus. Closer to the nucleus, the bending or the deflection will be more. Correct? Because the force of repulsion will be more. And you can see the ones which are extremely further from the nucleus, just going undeviated with no disturbance. And the ones which are exactly directed towards the center of the nucleus, they are the people who get deflected by more than 90 degrees. These were the observations. This is the previous page. No need. No need to draw this. Okay, right. So guys, write the evidence and the conclusion. Put it in a table. So here, angle of deflection is 0 to 10 degrees means it tells you what? Most of the alpha particles straight. Most.
So we have to write what you're writing, right?
No. Same thing I'm going to write for these people who are here. They can't see this one.
Oh.
Okay. Most alpha particles pass straight. With little deviation or no deviation. With little or no deviation. So what is the conclusion derived from that? The conclusion is most of the atom is empty space. There is a conclusion based on that. And the next one, the next observation is the angle of deflection is 0 to 90 degrees. So,
Go to the previous page again, it's still confusing.
wait. So the evidence is some alpha particles deflected through a large angle. So what is the conclusion based on that? A large concentration of charge in one place. There's a large concentration of charge in one place. That is a conclusion based on that. And there's another evidence. What is that? Some angle, some particles, some alpha particles are deflected by an angle more than 90. What does that tell you? What is the evidence? A few alpha particles are deflected back towards the source. Deflected back towards the source. That is the evidence. A few alpha particles are deflected back towards the source. So what is the conclusion based on that? Most of the mass of the atom and a large concentration of charges in a tiny central nucleus. most of the mass of the atom and a large concentration of charge is in a tiny central nucleus.
So I don't understand how we can get that conclusion from the evidence for the angles of deflection above 90 degrees.
The third one.
Yes, sir.
Okay, we got it. Two more than okay, right. Fine. The third point, the conclusion is like this. Now let's say is the atom. In that atom, there is this tiny nucleus. Okay. So whatever the alpha particles which were directed towards the nucleus, exactly towards the nucleus, when they come closer and closer towards the nucleus is positively charged. Alpha particles are positively charged. And also the nucleus has a mass. The alpha particles also have a mass. So between the nucleus and the alpha particles, there will be two types of forces acting. One is the repulsive force due to the charge, electrostatic repulsive force. Both are positively charged. Okay. Which is, and also there will be a gravitational force acting. That will be a very small force. The gravitational force is an extremely small force compared to the electrostatic force. So this electrostatic force will become bigger and bigger when they get closer. So when this gets closer, that force is big enough to deflect the particle and make it go back. Okay. So that happens for a very small percentage of alpha particles. Okay. So that tells you what? That central region where the nucleus is a very small area, because the other particles these are deflected this way. Okay. Understood.
Yes, sir.
Right. Okay. Right on the next subtopic.
So the alpha particle and the protons repel, right?
Yeah.
So then, do the protons get pushed in the opposite direction?
Yeah, within the nucleus can happen, but yeah, can happen.
Does it? Not.
Should, yes. Guys, write on the next subtopic. Representation of an atom. Representation of an atom. Right, this is nothing new. We have definitely done this for levels. And so guys, if you take an atom, you give two numbers here. This number is the proton number of protons. And this number, the one on the top, is the nucleon number. So what is nucleon number? Number of protons and neutrons. take it down and just label it. A is the atomic number of protons. B is the nucleon number, which is also known as the mass number. So the B minus A will be the number of neutrons. Right. There is a write down the next subtopic, thermionic emission. Draw this diagram. A coil connected to a battery. And just show that electrons are emitted. Okay. Because the word itself suggests thermionic emission. Thermal means, what is thermal? Heat. So thermionic emission means emitting electrons by heating a coil. Okay. So guys, when you connect it to a battery, when there's a current flowing through this coil will get heated. And if you can increase this voltage, if you keep on increasing the voltage, the current will keep on increasing. So the more and more this will get heated. So if it gets heated to a certain level or beyond that level, there will be electrons emitted. You call it what? Thermionic emission. So emitting electrons from a coil by heating it is what you call thermionic emission. Right under that. When a metal is heated, enough, when a metal is heated enough, it will emit electrons. It will emit electrons. Full stop. This is known as thermionic emission. This is known as thermionic emission. Right below that. Using these electrodes, and applying an electric field, using these electrodes and applying an electric field, comma, a beam of fast moving electrons, within brackets, cathode ray. A beam of fast moving electrons, you call it a ray of cathode ray. Close brackets, can be generated. Full stop. It is used in the CRO. What is CRO? Cathode ray oscilloscope. It is used in the cathode ray oscilloscope. An oscilloscope which uses cathode ray. An oscilloscope which uses a beam of electrodes. Okay, that's why you call it a cathode ray oscilloscope. So guys, write down a question. Write down a question. How fast an electron be moving? How fast an electron would be moving? If it was accelerated from rest. Through a potential difference of 2500 volts. Through a potential difference of 2500 volts. Okay, just draw the diagram. Okay, right. Guys, now stop your work and look at this. Now, this is the idea of the cathode ray. Guys, now here, this is the positive terminal. This is the negative terminal. You can see positive terminal of the battery is connected to this plate, and the negative terminal is connected to the metal filament. Okay, so this metal filament is at a negative voltage. This side is at a positive voltage. Correct? Electrons are positive, right? Electrons are negative. Very good. So guys, the moment this metal filament is going to emit an electron, what will happen next? Will it just stay here? Will the electron stay here at the filament?
It will be attracted to the positive.
It will
Okay.
accelerate towards the positive plate. Electrons are negatively charged. It will never want to stay at a negative terminal. So it will run towards a positive terminal. Okay, so these electrons are going to accelerate. So the question is what? Yes, it's going to accelerate. So the question is, how fast would an electron be moving if it was accelerated from rest to a potential difference of 2500 volts? So by the time it comes here, what will be the speed? Do you understand the question? Agreed? Fine. So guys, now there is an electric field strength between these two, where the potential difference is 2500 volts, right? But I don't know the distance between them, so I can't find the electric field strength. But I can find the energy that this electron will be getting when it passes through a voltage of 2500. So the energy, the electrical energy it is getting is E equals VQ, potential difference into charge. So the potential difference is 2500. And the charge of an electron is 1.6 into 10 to the power minus 19 coulombs. 2500 into 1.6 into 10 to the power minus 19 is 4 into 10 to the power minus 6 E joules. This is the energy the electron will be gaining. That is the work done by the electric field. That will be the form of energy that the electron will be having is kinetic energy. So the kinetic energy, the electron is going to have half mv square. So the half mv square is equal to 4 into 10 to the power minus 16. Half into, what is the mass of the electron? 9.11 into 10 to the power minus 31. That into v square is equal to 4 into 10 to the power minus 16. You don't have to memorize these values. All these are given in the data sheet. From here, we have to get the V subject. Can you do it? Which is see if we are getting this answer. Don't look at the screen, just look at it. Okay. Write down the next question. What is the wavelength of an electron? What is the wavelength of an electron? In a beam which has been accelerated, through 2000 volts, Guys, can you remember from your AS levels, for the particle, the wave nature of electrons or wave nature of particles, there was an equation which was connecting the wavelength and momentum. Lambda
De
equals
Broglie.
de Broglie wavelength. Very good. What is that equation?
Planck's
Lambda
constant.
equals h over p.
Lambda equals h over p. Do you remember this equation? Lambda is the wavelength which is associated with the moving particle. H is the Planck constant. P is the momentum of the particle. Correct? So I'm going to use that here. So the question is now, what is the wavelength of an electron in a beam which has been accelerated through 2000 volts? So when it has been accelerated through 2000 volts, I can find the speed just like how we did in the previous part. E is equal to VQ. So that E is going to be half mv square. Then V is 2000. Q is 1.6 into 10 to the power minus 90. Can you use that and find the speed that the particle will be gaining, the electron will be gaining? Just like how you did in the previous part. Can you find the speed of the particle? Okay, what is the speed? 2.65 into 10 to the power 20 minus 24. No. 10 to the power 7. Let's see. Yeah, I'm getting 2.65 into 10 to the power 7. Half into mv square, the kinetic energy gaining will be equal to the work done by the electric field, which is V into Q. So the V is 2.65 into 10 to the power 7. Correct? Right. It's 2.65 into 10 to the power 7. Fine. Then the momentum of the electron is mass into velocity. No? Momentum is P equals mass into velocity, right? So by using that, lambda is given by h over p. H is the Planck constant, which is 6.63 into 10 to the power minus 34. Okay. Over the momentum, momentum is mass into velocity. Mass is 9.11 into 10 to the power minus 31. mass, the velocity is what we just found now, 2.65 into 10 to the power 7. So that will give you the wavelength of the electron. What is it going to be? 2.75 into 10 to the power minus 11 meters. Okay, correct.
Sir, if they give this question without asking for V, can't we use E is equal to P squared over 2m instead?
Definitely you can. I didn't want to use it because if I use it, I have a feeling some people here will be even more confused. I can see some faces here already confused. I don't want to confuse them further. So that's why I just use this method. You can use that and find it totally fine. Okay. There is an equation connecting the kinetic energy and momentum and the mass E equals P square over 2m. From that you can, no? You can do that, no worries.
It applies to all particles, whether microscopic or
Whatever. Okay, fine. Any questions, anyone? Right, guys, write down the next question. Calculate the de Broglie wavelengths. No. Don't write that. Take the tube. The questions tube.
so. So when an alpha particle then if it hits the range, if it hits a shell, then won't it get attracted because the electrons are negative charge.
Tell again.
So won't an alpha particle attracted if it hits a shell of an atom because the electrons are negatively charged?
Yeah, possibly maybe there were, but there were no conclusions about it. Anything discussed in this
So
experiment.
why do shouldn't they get attracted?
Attracted to what?
Because there are electrons and then negatively charged and alpha particles are positively charged. Right?
Mhm.
Shouldn't they get attracted?
No, that impact is very minute at this. It's a very small. I mean, anyway, the electrons are too far from the nucleus. One reason.
No, not. What if they strike the nucleus like it's a like you showed when they strike the other regions of an atom, they get deflected, right? They get right? They are part right? So instead, why don't they get attracted with the electrons in the shells?
Yeah, that's what I'm saying. That the possible probability of that happening is very small. Because how the very limited number of electrons are there.
So in large atoms, there are
Yeah, but still not in the same level, no?
ah,
If you take one level, the first level, there will be only 2 electrons. Right, guys, turn to from page number 51 onwards, you will find MCQ questions. So go to those. Under that, question number 12 on page number 54. What's the answer?
It's
Which of
C,
is not a valid conclusion? Not a valid conclusion from the alpha particle scattering experiment. Most of the atom is empty space. That was a conclusion.
C.
Most of the mass of the atom is concentrated in the nucleus. That was a conclusion. The nucleus contains all the charge of the atom. No, that was never a conclusion. There was no statement like that. D, the radius of the nucleus is very small compared with the radius of the atom. Yes, that was a conclusion. That means the nucleus is very small compared to the size of the atom. So the answer is C.
So
That is
the
the
D wasn't a conclusion we wrote down, but that is a conclusion.
Sorry.
D isn't a conclusion we wrote down in the table, but it is a conclusion that we can
Yeah,
come
but
across.
no, we told, right?
Yeah.
The nucleus is small compared to the size of the atom.
Yeah.
So that means it talks about the radius. Then turn to question 24.
So which questions are?
24.
Oh.
The answer is, it's an obvious A. Which of the following describes why electrons are released from the metal filament during the thermionic emission? Because the metal filament is heated by an electric current.
So the
28.
most of the MCQs in UNIT come from particle physics.
Yes. Yes.
Does most of the structure questions also come from this?
No, not like that. It's a balance of 28.
D.
17.8. O is an isotope of oxygen. Which row of the table gives the number of nucleons and the number of neutrons in the atom? So guys, the number of nucleons is 17. Number of nucleons. So the number of protons is 8. So the number of neutrons will be 17 minus 8. That is 9. So the number of nucleons is 17. Number of neutrons is 9. The answer is D. Am I right? Okay. 30th one. Question 30. Maybe questions. In an electron deflection tube, electrons are released by passing a current through a metal filament. And what is the name of the process that releases the electrons? Thermionic emission. Correct?
So 31 is the same.
So question
Yeah.
number 1 is also the same.
31 and 32, can you answer those?
So 31 is the
Yeah, it's okay. 31 and 32. But it's connected to the diagram given. There's a diagram given above. So the 31 and 32 are based on that. That okay. Right. The diagram shows some of the components in a cathode ray tube. Electrons are released from the heated metal filament. Which of the following is the name of this process? So that is once again thermionic emission. The electrons releasing from a heated filament is what you call a thermionic emission. Fine. When a potential difference is applied across the parallel metal plates, the electrons are deflected. Which of the following changes would decrease the deflection of the electrons? Okay, guys, now listen to me. Now, these are two metal plates. So by the looks of it and what has happened, I can tell you, this plate is at a positive potential and this plate is at a relatively negative potential. Do you agree with me? Why? Because the beam of electron is getting deflected towards the up plate, the top plate. So that means if electrons are negatively charged now, then definitely this top plate has to be having a positive voltage. Okay. Now what are they asking is, they have given 4 options. Out of these, which of the following change would decrease the deflection of the electrons? Let me check one by one. Increasing the current in the metal filament. If you increase the current in the metal filament, what will happen? This filament will get heated more. When the filament gets heated more electrons will be emitted. Correct? But whatever the electron that is going through this, it will going through the same potential difference between the parallel plates. Same potential difference, same distance between the plates. So the same electric field strength between the plates. So the deflection will be the same. So increasing the current in the metal filament has nothing to do with the amount of deflection. Do you understand that? Exactly. Yeah. So no. Increasing the distance between the plates. Now guys, if I increase this, if I move this plate here and this plate here, and if I increase the distance between them, then what will happen to the electric fields between the plates? It will reduce. Am I right? You increase the distance between two metal plates, the electric field strength between them will reduce. If the electric field strength between the plates is reducing, means the force exerted on the electrons when they are moving within the plates will be reduced. So that will lead to less deflections of electron. Agree? If you increase the spacing between the metal plates, the strength of the field will reduce, electric field. So the force on the electrons will be less. So the amount of deflection happening for the electrons will be less. So yes, that is, we can agree on that. Increasing the distance between the plates will decrease the deflection of the electrons. Anyway, let me check the remaining two statements. Once again, increasing the length of the plates has nothing to do with the amount of deflection. Correct? And increasing the potential difference across the plates. What will happen then? If you increase the potential difference between the plates, that means you are making the electric field between the plates stronger. If you make the electric field stronger, the electrons will be experiencing a higher force. So experiencing a higher force means they will be deflected even more. That will lead to a higher deflection. Am I right? So the answer is B for banana. Right. Right. Question number 39. And 40. 39, 40, and 41. Right, where's the 39th? The diagram represents an arrangement to demonstrate electron diffraction. A beam of electrons is directed at a sample of crystalline material. Which of the following
Is it B, sir?
Which of the following single change would decrease the angle of diffraction theta? Would decrease the angle of diffraction. Decrease the distance between the sample and the screen.
So that will create a bigger angle, right, sir?
Let's see. Increase the anode potential V. This one.
That
Increase
will
the current in the
accelerate it more.
use a sample with a small atomic spacing. What is the answer?
B.
D.
Hold on. This is actually connected to diffraction that we learned. Read the question again. A beam of electron is directed at a sample of crystalline material. Which of the following change would single change would decrease the angle of diffraction, which will reduce the angle of diffraction? Decrease the distance between the sample and the screen. That is definitely no. That is not going to make any difference, no. Just because you bring this screen here, the path will be the same though. The angle depends on whatever that is happening within the sample. No. Just because you bring the screen closer, what is happening inside the sample is not going to change. So that will not make any impact on the angle of diffraction. Okay.
So that is actually maths, not physics.
Increase the anode potential V. So if you increase the anode potential V, that means you are giving more energy for the electrons. So if you give more energy for the electrons, that has nothing to
Wouldn't it accelerate them?
give me a minute. Lambda equals H over P. See, statement C, increase in the current in the filament. Once again, the increase in the current in the filament has nothing to do here. Increase in the current in the filament will just make the number of electrons increase. Okay. Use a sample with a small atomic spacing.
No, that will be worse. It will create much bigger and worse.
Yeah, if you have a sample with a small atomic spacing, they're asking which would decrease the angle of diffraction. If the atomic spacing is smaller, the angle of diffraction will be more, right? Mhm. Give me a minute.
What are NMB?
No, no. Wait, guys, it's like this. Can you remember for the diffraction to happen, the angle of the diffraction will be noticeable when a wave is passing through a aperture. The diffraction will be noticeable if the wavelength is approximately equal to the aperture width. Can you remember this from your ES levels? Okay. So if the atomic spacing is less, the diffraction will be more actual. It will be more diffracted. Okay. The diffraction will be more. So actually it has to be B. The reason, increasing the anode potential, if you increase the anode potential, by the time the electrons get here, their speed will be more. The speed is more means their momentum will be more. Their momentum is more means their wavelength will be less. Okay. So then I go with the answer B, but anyway, I will check on this and get back to you. I will go with B for now. The 40th one. So this is talking about the diffraction, right? Okay, leave that for now. There's a 40th one. What is your answer? The diagram shows two metal plates with a potential difference V across them. The path of an electron traveling between the plates is given. The electron is deviated through an angle theta. Which row of the table shows the changes that will cause theta to decrease? Now this is about the deflection. Which row of the table shows changes that will
Is
cause
it Caesar?
theta to decrease? That means the deflection to decrease.
Is it
So the
C?
path will be something like this. Let's see. If you double the V, that is going to increase the deflection. If you increase the voltage, if you double the voltage, deflection will be more. But if you make the voltage half, like we discussed earlier, when you reduce the voltage, the deflection will be less. And also, if you increase the distance between the plates, if you double the distance between the plates, that will also once again reduce the deflection. So the answer has to be C. Okay. Any questions?
Can you exactly explain what's the difference between diffraction and diffraction? Kind of.
Now you get it. What is deflection, right?
Yeah, I get
The path getting changed, that is deflection. Diffraction is when a wave is passing through a gap. It spreads out.
So
That is
real path can change.
Yeah, that is for a wave, not for a particle.
So diffraction is the diffraction of particles.
Diffraction is the change of path of a wave when it is passing through a gap.
So then if you apply diffraction for particles, it's called diffraction.
No. Deflection, it doesn't have to be diffraction, no, it doesn't have to be passing through something. Deflection can happen anywhere. 41st one. In 2016, the element organism was added to the periodic table. Oh. One isotope of this has a symbol given. Which row of the table shows the number of protons and the number of neutrons in a nucleus of this isotope? So guys, number of protons is 180. Number of neutrons will be 294 minus 118, which is 176. The answer is A. Correct. And then thirty-sixth one. Thirty-sixth one. What is the answer? In the early 20th century, scattering experiments were carried out by directing high-speed alpha particles at thin metal foils. Which of the following could not be concluded from these experiments? Could not be concluded. Most of the atom is empty space was a conclusion.
So D.
The nucleus of the atom is positively charged. Hold on. C. There is a concentration of charge in the atom. Yes, that was a conclusion. D. There is a concentration of mass in the atom. Yes, that was a conclusion. What was not a conclusion? The nucleus of the atom is positively charged was not a conclusion from that. Now we know that it is positively charged. But then in that experiment, what was derived is read the conclusion and see that it is charged. There is a charge concentrated at the center. But you didn't know whether it is positive or negative or what. So they're asking based on that, at that time, in the early 20th century, based on that experiment, what is not a conclusion? So based on the options available, that's B. Okay. No. Because why? Used any alpha particles, right? At that time, maybe they didn't know that alpha particles are positively charged. You get it? So you know that it is charged, but you don't know what it is. Right. Anyway, out of the 4 options available, I definitely can't choose A, C, or D. Those were obvious conclusions from that experiment. Correct? Which one is that? Yeah, what we did, right? Right, guys, then question number 8, page number 30. Read the question. Right. In the early 20th century, experiments were carried out in which alpha particles were directed towards the same goal file. A simplified diagram of the apparatus used is given below. State 3 observations and the corresponding conclusions made from the alpha particle scattering experiment. 6 marks. Try to write a decent answer that will get you the entire 6 marks. Let's write. So I will put up a table here. Observation, conclusion. Yeah. Okay. First one. Most of the alpha particles were undeviated or slightly deviated. Most of the alpha particles were undeviated or slightly deviated. Okay. So the conclusion based on that. Most of the atom is empty space. Most of the atom is empty space. The next observation. A small percentage or a small amount of alpha particles were deviated by the acute angle. Okay. Right. Then you can see the charge, the more a high charge or a charge is concentrated in the middle. A high charge is concentrated in the middle of the atom. a very small amount of alpha particles were deflected more than 180 degrees. So the conclusion, the mass or the most of the mass
So how are the particles deflected more than 180 degrees?
wait, more, sorry, more than 90 degrees, what did I write? The most of the mass of the atom is concentrated in a tiny region in the middle. The most of the mass of the atom is concentrated in a tiny region in the middle. So definitely this will get you the 6 marks. 3 marks for the observations, 3 for the conclusions. Okay. There's part B.
So why are we learning all this stuff, sir? Those times, this is what scientists were learning, while children were learning more important stuff. And we are learning
Your,
what scientists are coming
yeah, your
across.
question is why we are learning now. The reason why you are learning is because you decided to do Edexcel A level. Okay.
You don't other syllabuses also have this.
Cambridge doesn't have this part. Right. Here's part B.
Yes, this is interesting.
Yeah, it's like this. Different people like different things with this. Now, you should understand physics is like an ocean. Okay. From that ocean, if you put a bucket and take a bucket of water, that is the A-level physics what you learn. Okay. What you learn is super little. If you feel like already know I'm a scientist, BS. Okay. You are just learning a bucket from an ocean. Right? So this bucket has different departments of physics. There is some topics we have done related to mechanical, some topics we have done related to particles, some topic related to waves, electricity, and whatnot, and astrophysics. Okay, so physics has so many different branches. So if you like to pursue in a separate field, you can do it after A levels. Okay. So what you do for A levels is from different sections they have taken and put different parts for you to see what you like to do. Now it's strange. There are people who actually like this. I don't know whether this guy who was there earlier, the AS batch, he did last year AS and A2 together. Menath. He is going to do a degree in particle physics. Okay. There are people who like it. So there are people who like astrophysics, but definitely there's no future for those people in Sri Lanka. Okay, definitely no. I can guarantee you that for the next, at least for next 30 to 40 years, there will be no future for those people in Sri Lanka. There won't be a career in Sri Lanka, but internationally, yes, definitely there's a huge scope. Because it's a connection between the demand and supply. There's a good demand, but the supply is very little at the moment. So if you continue to study this, there will be high demand for you, but somewhere in some corner of the world, but not here, unfortunately or fortunately. Right? Fine. Part B, one experiment. Read the part B.
Second one, right? How is the second one related to the nucleus as well? Only the third one is right.
No, a small amount of alpha particles are deflected, having a deviation by an acute angle. That's because electrostatically there is a repulsive force. So that means there is a mass concentrated in the middle. Sorry, charge concentrated in the middle.
Wait, so the second one is also related to the nucleus.
Yeah, all the third one is also related to the nucleus. Right. One experiment.
So by the same nucleus, like some particles deflected by acute angle and some.
Yeah, one who deflected by more than 90 degrees are the gold alpha particles which are directed towards the nucleus. So that is very small, means that mass concentrated area is very small. The nucleus is very small. Get it?
The second category is directed towards the nucleus, but
Not directed exactly towards the nucleus. Not correct. One experiment used gold foil made from the gold isotopes 19779 AU. The alpha particles had an initial kinetic energy of 4.7 mega electron volts. Show that the closest distance these alpha particles can get to a gold nucleus is about 5 × 10⁻⁴ 14 meters. Okay, we'll do this and take a break. Look at this. Guys, there is a gold nucleus. Which has a charge of 79 protons. 79 protons. Okay, a positive charge. And there is this alpha particle. Yeah, listen carefully. Alpha particle, guys, you know that it has 2 protons. And you know that charge of a proton is plus 1.6 × 10⁻⁻19 coulombs. The same as the charge of an electron. Electrons are negative, protons are positive. So the alpha particle consists of 2 protons. So alpha particle is positively charged. And this gold nucleus is having 79 protons, which is also positively charged. Correct? Now, these alpha particles are directed with an initial kinetic energy of 4.7 mega electron volts. So they will travel towards the gold nucleus. By the time they travel towards the gold nucleus, their kinetic energy will reduce. And there comes a point, their kinetic energy will become 0. Am I right? So when they come to that point, at that point, the entire kinetic energy has got converted to electric potential energy. So they want you to find what is this distance, x. Show that the closest distance these alpha particles can get to a gold nucleus is about 5 × 10⁻⁴ meters. Correct? The electric potential energy is given by what? E equals 1/4 pi epsilon naught Q1 Q2 over R. Do you remember this? Electric potential is given by what? Electric potential. KQ over R, right? K is 1/4 pi epsilon naught Q over R. So electric potential energy is given by what? That potential multiplied by the charge. So 104 pi epsilon naught Q1 over QR is potential. That multiplied by the other charge is potential energy. So look at this one. That is going to be equal to the kinetic energy, 4.7 mega electron volts, this had. So guys, 104 pi epsilon naught is what? 8.99 into 10 to the power 9. Okay. The value of K. It's there in the data sheet. And I think I have given this value as well. 104 pi epsilon naught is 8.99 into 10 to the power 9. One charge is 79 into 1.6 into 10 to the power minus 19. The other charge is 2 into 1.6 into 10 to the power minus 19. That divided by the X is the R that I need to find. So this is going to be the electric potential energy that will be equal to 4.7 mega electron volts. 4.7 mega electron volts mean 4.7 into 10 to the power 6 electron volts. Correct? How do you convert electron volts to joules? Multiply by the charge of an electron, which is 1.6 into 10 to the power minus 90. Solve this equation and find the X. That will be the answer. The next one is easy. Calculate the strength of the electric field due to the gold nucleus at this distance. Guys, did you get the X as 4.835 into 10 to the power minus 14? Don't copy my values. Okay. Next one is to calculate the strength of the electric field. Electric field strength is given by E equals 104 pi epsilon naught Q over R square. So 8.99 into 10 to the power 9 is the 104 epsilon naught. The charge is, they are asking the strength of the electric field due to the gold nucleus. So it has 79 protons. 79 into 1.6 into 10 to the power minus 19. Over the distance, we just found it to be 4.835 into 10 to the power minus 14, and that's square. Four 4.86 into 10 to the power 19. Newtons per coulomb or volts per meter. That is the electric field strength.
And forgot the ratio. This C and this C are same. These two V's.
No. That one is the electric potential energy. So if it is confusing, I will take it as EP. This is electric potential energy. For energy, I have taken E. This is the electric field strength E. Right, guys, take a break. See you in 15 minutes.
They have quite similar equations.
26 letters Guys, question number 25, mark it for homework. '25. Okay. Write down the next subtopic. Particle accelerators.
So 25 is homework, right, sir?
Yes. Particle accelerators. So guys, the name itself says what it is. So that is a device which is used to accelerate particles. Okay. A device which is used to accelerate particles, you call it a particle accelerator. It accelerates particles. There are two types. I don't know whether there are more, but in the syllabus there are two types of particle accelerators. But to what I know, no, there are only two types of particle accelerators. One is a linear accelerator. The other one is a circular accelerator. Okay. Under that, write down the subtopic. Linear accelerators. Okay. Right under that. A simple method to accelerate particles. A simple method to accelerate particles is a linear accelerator. Is a linear accelerator.
So they use the circular accelerator in I think UK or something to try to recreate the Big Bang, right?
Not only in UK, I think more than UK, it happens in US. Okay.
US, sorry.
Happens not only even in Russia, even in China, I think even Japan. So all those countries are using particle accelerators. Right. A simple method to accelerate particles is a linear accelerator. Full stop. The particles accelerate through a series of cylinders, and the polarity of the cylinders keeps changing. The polarity of the cylinders keeps changing as they are connected to an AC voltage. As they are connected to an AC voltage. Full stop. The frequency is very high. The frequency is very high. The frequency is very high. And it changes the polarity of the cylinders. the frequency is very high and it changes the polarity of the cylinders so that particles accelerate continuously. Okay. The length of the cylinders gets longer. The length of the cylinders gets longer and longer. Since the distance traveled by the particles, in a unit time keeps on increasing. Okay, right, guys, just read what you have written. I will explain it. Okay, so particle accelerator. Now look at this diagram. This is a linear particle, part of a linear particle accelerator. Okay. And from the left corner, what you see is the electrons injected into this first cylinder. So guys, electrons are negatively charged. So then if you want the electrons to get attracted towards this one, so this cylinder should be at a positive voltage. Am I right? And the electrons will go through this, accelerate, and goes through this. By the time the electron comes to this corner, the polarity of the cylinder will change. This will become negative. This will become positive. Understand? Then electrons will now move away from the negative cylinder and gets attracted to the cylinder B, which is positive. And then it gets attracted to B and it moves through B. And once it reaches here, then the polarity will switch. Now the B will become negative, C will become positive. Understand? So look at the arrangement. It's beautifully connected. Here, see? All these are at 1 voltage. This one, look at this network. All these cylinders, the alternative cylinders are at 1 voltage. A, C, E, these 3 are in 1 voltage. Look at the other ones. B, D, and if there's another one after this, F, those are at 1 voltage. When A, C, E is positive, B, D, F will be negative. When A, C, E is negative, B, D, F will be positive. And that's how they are connected to the alternating current supplier. One is connected to one side of the supplier. The other branch is connected to the other side of the supplier. So you know an alternating current supplier keeps changing its voltage polarity, right? Positive, negative, it keeps changing. Okay. So the frequency of the alternating power supply here, the alternating current supply here, is chosen so that by the time it comes to that corner, the polarity will change. Okay. That's how the frequency is decided. And also the length of these cylinders, you can see, keeps on increasing. Why? Why? Because the electrons are accelerating,
It's a
right?
particle accelerator, so it's keep on
Yeah.
accelerating.
Particles are accelerating, their speed is increasing. So the distance they travel in the first second is not the same as the distance they travel in the second second. So that distance is keeping on changing. So now let's say for an example, for the electron to move from through the cylinder A, it took, for an example, let's say it took 0.01 second. So from B to cross B also, it should take 0.01 second. Exactly the same time. But during that time, now the electrons are going to travel a further distance. So the length of the cylinders are chosen in such a way that sinking will properly happen. Understood? Exactly. Yeah. So the length will keep on increasing. That's because the distance traveled by the particles is keeping on increasing. It is particles accelerating. That is what explained in the question, the note. You can read it again. This is what a linear accelerator is. Come again? Yeah. Definitely. It's not six, it's just one small part. There will be so many of these, not just six. This is just one part of the linear accelerator. This. I think it's better if you can draw it just for once. Can you?
So what's that like S sign?
That is alternating power supply, right? Slight curve in what? You mean in a cylinder, is it? No, then it will not function. It can go and knock the wall of the cylinder and it will not sync properly. The time and the distance travel will not sync. So, sir, hold on. That is alternating current supply. Alternating power supply. Actually, guys, write your names in the tube, in the maybe inside our page. Keep your names. Sometimes people misplace it and you can't find it. Keep it in. Maybe there should be some particle maybe using a voltage, high voltage and thermionic emission or something. I don't know. Can be. I don't know that they have advanced ways of it, but if you even have a way of thermionic emission, you can generate electrons. But I don't know if they have advanced way of doing it. Okay, right, guys, and that's it for the day. There are enough questions based on this linear accelerator in the tube. We will do those in the next class. Okay. Have a nice week, eh? See you next week. Bye, take care. What is the practical application? Linear accelerator itself is why the particles are accelerating?